Everybody's here. And files. Okay, first of all, let's, any questions on the project so far? Like I said, you've seen all the pieces. You hadn't seen them put together this way. So you have to determine path length, for example. I've given you location information. The path calculator will actually give you length. A couple of things that I've heard from people: be careful using the path calculator. Remember that when I had the slides that taught you how to use it, I had you change some parameters. So the defaults work fine, they're just not the units we showed. So for example, the default is to use meters instead of feet. Be sure you change that. If you're going to expect to speak in feet, be sure you change it to feet. Similarly, the default, I think the default in there is to use megahertz instead of gigahertz, things like that. It defaults to not selecting a particular Fresnel zone, and the way the display I showed you requires that you set it to show the 1.0 Fresnel zone, the first Fresnel zone. So just be sure you handle all of those. Remember that you are not trying to guess what I would do. You are doing the math to evaluate the problem. You are using the information I've provided you in there to make a decision on what the system should look like. There's more than one way to build this successfully. Which way you choose depends on how you interpret the information I've given you. And, you know, you have to justify it. But I'm not going to say there's one exact way to do that. You'll never hear me say that about a problem in this industry. So be sure you justify your decisions and why you want a particular way. That's as important as doing the math correctly. Okay? So no questions on the project? Okay. Well, in that case, let's jump into the fascinating world of PAN technologies. Of course, we don't go through every technology out there. In this particular case, I should have said low-speed PANs on this, because that's what I'm showing in this presentation. This is basically Chapter 5, and we'll look at high-speed PANs next time. Realize that a PAN, as a general term, accomplishes a couple of specific things. It is designed by definition to be a very short-range network. It accomplishes short-range communication for a particular reason. The differences between the protocols reflect what that application is. And we're going to look at a couple of them here, talk about that. Friday, we'll look at a couple of the others and look at the differences and then kind of do an overview on all of them. Okay? So, the first one we're going to look at is the one that probably everybody in the world has heard of. It's called Bluetooth. If you'll recall, we talked about the IEEE 802 project and 802.15, our personal area network projects. This was started in February of 1980, I think. Not even sure I put it in here. No, I didn't write it in this one. I think it was February of 80. But anyway, over the years they've defined PANs, they've defined interaction between PANs. Bluetooth is 802.15.1. It's a specific sub-protocol of the PAN part of it. It has a specific application. It's made to replace cabling for user devices. So, you know, you've seen the people walking around with a, you know, it looks like a clothespin clipped to their ear, talking to themselves. You know, they've got a Bluetooth headset on, connecting to a phone in their pocket. What they're replacing is a wired connection between that phone and the headset they're using. You've seen people using wireless keyboards or wireless mice. You know, we actually don't have one in here, but if I don't want to have this tether, for example, for some reason, like in the auditorium, we can use Bluetooth to carry that. Okay, when we start looking at that as the application, then we can make some assumptions about what this protocol has to accomplish. We're probably not looking at really complex networks. You know, that's not the goal here. The goal is to not have to lug around, at the time this protocol came out, a serial cable or two with different ends on it, a headset cable, things like that. It was so I could walk up or I could use devices without having to actually cable them together. That's all it needed to accomplish. So with that in mind, let's start digging into it a little bit. When they put this together, they decided to put it in the 2.4 gigahertz band. 2.4 you see come up a lot, and there are a couple of reasons for it. Biggest one is it is a license-free assignment. It's the first license-free assignment as you go up in frequency that actually has a lot of bandwidth, that'll actually support wide bandwidth applications. The 903 to 928 spectrum can, but it's not that wide. That's 25 megahertz. An 802.11 channel is 20 megahertz wide. So this is the first allocation we have that has lots of elbow room. Putting it there is a little bit of an accident of timing. Bluetooth is actually older than recognizable forms of 802.11. And so this existed, and then 802.11 came in on top of it. Now the problem is, those two, plus microwave ovens, plus a bunch of other stuff, exist. Zigbee exists, and we'll look at that, on the same frequency, and they can interfere with each other. If you've used an older Bluetooth device along with your Wi-Fi network, you may have noticed that. I have an older Bluetooth keyboard at home that I love. It has, it's one of those that has a great feel. I don't want to get rid of it. But it's the old Bluetooth standard that didn't do some of the tricks we'll talk about in a second. When I turn it on and I use it with a notebook computer and I'm a little far from my access point, it'll knock down my transfer rate because it'll wipe out part of the 802.11 signal. The modulation schemes are very different. 802.11, depending on what you're using, uses very wide channels. There's our standard 1, 6, and 11. We'll look at why that is what it is when we get to 802.11. Bluetooth uses straight frequency hopping. So we generate a modulation scheme that is codes bits, and then we change the carrier frequency for that pretty rapidly. There are 79 channels, and if you notice, any given channel actually isn't much of an 802.11 sequence. The problem is, the way Bluetooth devices coexist is they choose a random hopping sequence. So my Bluetooth device and yours are going to connect. When we make that connection, and we'll look at how it happens here in a second, when we make that connection, we randomly choose what order we're going to use those 79 channels. So it might go 1, 30, 72, 16, so on and so forth. The next connection that comes up, we'll choose a different random sequence. And the idea is they're all hopping at about the same rate. The chances of them randomly selecting the same channel simultaneously are pretty slim, and the chances of it happening twice in a row or enough for two to bother each other are slim squared. Of course, as you get more and more devices going on it, that's not true. As you get more and more Piconets, different sets of associations going, the chance of that happening goes up because you've got more devices trying to use the same channels in approximately the same way, and so it gets more likely that you're going to have interference then. 802.11 actually sees this as narrowband interference, and it's pretty good at dealing with it. The problem is if that random hopping sequence concentrates a lot of the channel usage inside one of the 802.11 channels, now you've got several narrowband noise signals from the point of view of the 802.11 channel operating within its bandwidth. What happened later on is they came up with something called adaptive frequency hopping, and basically the newer versions of the protocol know how to listen to the spectrum and see if there are other devices on there. They don't know how to decode like 802.11, but they can listen to see if it's there. And it's good for both the avoiding interference to 802.11 and getting interference from 802.11, because it works both ways. It's also good for avoiding microwave oven stuff. Badly built microwave ovens tend to wipe out the bottom third of this spectrum. If I have time in this, when we get into the 802.11 section, I'll bring a spectrum analyzer in here and then fire up a microwave oven. You'll see it just lights up on one end of the channel spectrum. Okay, so we've got frequency space at 2.4 gigahertz, 79 channels. We jumped through them. What we're doing from an OSI point of view, OSI, of course, defines the physical layers, layer 1, and the data link layer is layer 2. Physical layer is basically how I signal a bit across a particular physical medium. Okay? How do I represent a bit to you? And how do you detect the bit when you're connected to that medium? Layer 2 deals with how we share information and how we package information that was packetized and hand it to the physical layer to send one bit at a time. So layer 2 actually has a pretty complex task ahead. Both of those are sufficiently complicated that the standards in here and the IEEE standards actually break both of those layers into two pieces. They'll break the physical layer in what they call the physical media dependent section. That's the lower half. It actually is physically how do we connect to the medium. If you're talking coaxial cable, it defines the connector. If you're talking RF, it defines the frequency, et cetera, et cetera. The upper half of that deals with how we take this frame sequence, whatever the frame defined at layer 2 is, how we take that and hand it to the physical media dependent part one bit at a time, or in a way that it can send it one bit at a time. So it's the coordination between the actual hardware and the protocols at the upper level. In 802.11, this is implemented in a radio module. In fact, both layer 1 and layer 2 are implemented in a radio module. We'll come back to that in a second. Similarly, layer 2 is broken into two pieces, and there are a couple of things that it has to do. It has to generate a signal that is in a framed format that it can handle layer 1. That's what this baseband is. It's that framed bit representation of whatever it is that's come down from the upper layer protocols. It also defines how we're going to talk to the application part of this, which is written in to talk to the network layer and all of that. All of this resides in OSI layer 1 and 2. The application profiles and how we actually use this stuff and how we do end-to-end communication and all that reside further up, and that's in your computer drivers or the device drivers and whatever you're using. We're going to focus on these two in here. When we do Bluetooth, remembering that it was put together to replace cabling for consumer devices, we have a couple of basic things we can do. Audio is always a part of it. So when you're using a Bluetooth headset or a wireless microphone that uses Bluetooth, you're actually using one particular type of transmission called an SCO. It's a synchronous connection-oriented link. If you've had telephony, you're essentially talking about a DS0. What we're doing is taking coded audio at 64 kilobits a second, and I'm handing it to you in a synchronous stream. In other words, I don't send it packetized, I send it as a continuous stream of bits across that link. And I'm talking about from the upper layer here, I would have my coded audio coming in here. I'm not actually coding audio here, I'm just accepting audio that is already coded at an upper level, and then I move it across this channel at 64 kilobits continuously. I'm not packetizing it. Data, because it doesn't have to have that immediacy, it doesn't, let me rephrase that, because it's not as critical for delivery, actually uses a packetized type of channel. The reason we use synchronous and circuit-oriented for audio is, what do if I get an errored frame and I ask for a retransmission in audio? What good is it going to do to come back and put audio from half a second ago back in the stream? There's no reason to do that. It's out of order. It doesn't make any sense. It's actually worse than just leaving it out. Data's not that way. I can go back and reassemble it. So in that case, we use, I'm sorry, I didn't define it. The audio link is called SCO. That's that synchronous connection-oriented connection. We can move data across the SCO, and if you have data that needs to move in both directions at the same speed, that would be audio, duplex audio, then you can do that. Most data applications don't work that way. Coded voice does. If I'm talking to you on the phone, I want to be able to hear you at the same time I'm talking to you. And so we run that stream, the same amount of data both directions, all the time. Most true data applications, I'm sending you a picture or I'm sending you a file, one direction is going to need more bandwidth than the other. You're going to ask me for a file. Small request. Send me this file. I'm going to dump this big file to you. So in that situation, really, for the communication, we just need a little bit of data bandwidth coming from you to me, but a big pipe from me to you. If we reverse that, then we need that channel to reverse. And that's what you get when you look at what they call ACL. They're asynchronous connectionless links. This is the kind of communication you're used to from Ethernet. I'm packetizing it. I'm sending it asynchronously. So if I don't have anything to send, I don't use the channel. And I'm not maintaining an open channel between us. Each packet is delivered independently across that. That's what asynchronous connectionless means. The two variations of ACL simply flip-flop which one's high speed. We've got, let's see, did I put in? No, I didn't. We flip-flop how much bandwidth there is. Basically, the low speed in an ACL, the low speed channel moves at 57.6 kilobits. The high speed channel moves at 723 kilobits. If you do it the other way, you flip the direction. That's all it is. Now, once we do that, and we've got layer 1 and layer 2 defined, we implement all of that in a Bluetooth module. And you've seen these. These are these are truly tiny. It's the connector for the USB port is larger than the radio itself and the antenna. Why? It's short range. I'm going from the top of this desk 2 or 3 feet down. The most common power level in this is 1 milliwatt, 0 dBm. I mean, this is a very, very, very low power system. Part of that is because the assumption was they're going to be run by battery. And higher power means shorter battery life. You can actually crank the power up if you need. They call them level 1, level 2, and level 3 devices. Once we do this, what we have is a module that connects to your application level in your device. I'll consider it a computer because it's a little easier to talk about. From layer 2, it plugs it into your computer's layer 3 protocol, however it's going to do that. And it just says, here it is. Deal with it. Make it come out somewhere. Remember, this is a layer 2 protocol, so it only knows about the local network. It doesn't understand that there are other networks out there. When you have devices connected together, you create something called a Piconet. Again, the goal is very short range, a few devices. I might want to connect a keyboard and a wireless mouse, maybe a headset, game controller or something like that. I don't need a lot of devices. And in fact, I'm limited to one master device, the one that I'm going to connect things to, and 7 slave devices. I'll let you read it in the book. They're pretty common sense things. Active slave means one that's actually communicating. Parked slave is one that's in a low power mode. It's not actively being used, so it powers down. I'll let you read about that. When you put these together, all of those go together as a star network with the master in the middle. And doing that means that each one of those carries a one-to-one communication between master and slave. Each of the slaves carries on a one-to-one communication with the master. If you've ever done any of this, the first thing you have to do is turn on the devices, and usually you have to type in some sort of code or accept some sort of code or something like that. And what you're doing is accomplishing pairing. Remember, this is an open connection for peripheral devices. So why would I want to let you connect to my computer without having some control over that? And the control was, you put the 2 devices out there. The master device and the slave device have to agree on a pin. The pin is simply, it's not ASCII, it's Unicode, but it's basically a text sequence. I have to send, the master sends it to the slave replies with the same pin code. If pin codes don't match, they don't pair. It's that simple. The idea is that I control what pin code the slave has to use to associate with the master. Now the problem is a lot of these devices don't have a way to put a pin code in. How are you going to type a pin code into a wireless headset? You can't. Or you could use Morse code or something. Why would you do it? So the problem is, I say it's a problem, it actually becomes a problem. What they do is they'll simply preset the pin code. And they'll say, okay, the pin code for this one is 2222. So when you want this to pair, the master has to reply with 2222. It doesn't actually matter which end of this initiates the setup. That's fine. It makes it easy to do devices like headsets. But if you know that AT&T's model, 4702 wireless headset uses this pin code, you know how to connect to my master with it. Now, I have to reply to that, but you could social engineer around it. And that's where the problem comes in this. We'll look at the security on this. Actually, later versions of the protocol implemented public key transfer like you've done. And so it gets around some of this. You need to be aware of it. This is a problem for car manufacturers. I have a car that has a Bluetooth system, and I love it. I can take my iPad and play music through the car, and I can take my phone and pair it so it plays through the sound system. That car is inviting others to connect to it, and they've actually been studying. I so far haven't heard my particular make and model of car, but there are, I'm trying to remember where it was, I think it was UC Berkeley. A couple of computer scientists managed to take over a car using the Bluetooth interface, even though it's not supposed to be able to be done. You guys know enough security to know how strong that statement is. So consider, from a car manufacturer's point of view, there's the potential out there, because of this kind of vulnerability, for me to drive up beside you, get into the computer network in your car, and decide just how fast you ought to be driving, which sounds like a lot of fun. There was a guy, I'm going to digress for a second, there was a guy that used to work here. He was kind of my mentor on some things, and truly a brilliant man. He was funny as he could be, and he was just scary smart. He came up with a way to deal with road rage. He said, everybody wants to shoot people. He said, so what we're going to do is mandate putting a receiver in every single vehicle on the highway. And we're going to give everybody a plastic gun that shoots a laser or whatever. And he said, if you do something stupid, then I'm going to point at your car and shoot. And if you collect, 5 shots in 10 seconds or something, your car shuts down for 2 or 3 minutes. That's pretty brilliant, Of course, I could see high school kids putting 6 of them in a car with 6 guns and go, Anyway, I thought that was a pretty brilliant way to deal with it. This is one Piconet. We can actually extend this. This has always felt to me like an afterthought, but you actually can extend this network structure by letting one device connect into 2 different Piconets. Piconet basically is a group of devices that agree on that hopping sequence. Okay, so we're communicating there. What I can do is let one device belong to 2 Piconets. Now, there's some limitations. A single device can't be a master in more than 1 Piconet. It can be a master in 1 Piconet and a slave in another one. It can actually be a slave in more than one more. I have never seen this actually done. I'll take their word for it that it's possible. It seems to me, because you're making this device change how it thinks about a network. When it's a master, it's controlling the communication process. When it's slave, it's being controlled. So there's one change. It's changing hopping sequences at the physical level. That takes some finite amount of time to do, because you have to synchronize every time you change. And so it's always seemed to me that this would introduce an enormous amount of latency to do this. Now, that's not a practical comment. That's just my assumption. Sometime I'll find a device that claims to be able to do this, and we'll play with it and have some fun. When you do this kind of thing, what you've created is a scatter net. Again, I've never seen this actually implemented, so I'm not. If you know of one, I'd like to know, but I've never seen one. Because the goal of this protocol was pretty simple. We're going to allow peripheral devices to connect over a very short range to a master device. And I'm really kind of thinking, how do I do this as a single user for my peripherals? The frame structure is very simple. Excuse me. We basically have 3 pieces of it. One of them is the access code essentially manages the hopping sequence and identifies which Piconet we're on. The header does what headers typically do. Where are we? What's the, what are the choices we made and set up? And then you have user data. It doesn't support complex networks because it was never intended to do that. That's why I say I think this is an afterthought. Oh, wouldn't it be cool if we could mash 2 of these together? I think it was probably about that level. So anyway, Bluetooth. The other one that a lot of people haven't heard of, you guys may or may not have, is Zigbee. Zigbee is another 802.15 protocol, but it is 802.15.4. It was also, because it's a personal area network, it was designed to be very short range. These aren't supposed to go very far. But the goal of this one was different. The goal of this one was to replace instrumentation-style connections. So I'm going to need to move relatively small amounts of data, but I may need to build relatively complex networks. If I'm going to use this to control a process, for example, I might have to have 3 or 4 different streams of how things work. I might want to have a group of machines here that can communicate, another group that can communicate over here, and occasionally the two groups have to communicate. That's a very different problem than connecting a few peripherals to a central device. Zigbee, when it was defined, watched and learned. They saw the problem with Bluetooth and the 802.11 stuff, and so they actually defined frequency space in 3 different frequency ranges. Lowest is a frequency actually nicely sandwiched between the two halves of the cellular spectrum. Cellular actually works from about 870 up and about 865 down, and they're paired in channels that way. So right in the middle of that, this nice little clear slice in the middle that was supposed to be guard band, they said, yeah, we'll let you use 600 kilohertz of it. We also define 10 channels in the ISM band at 915. Each of those has 2 megahertz of bandwidth associated with. The one at 868 is just a single channel. And then at 2.4 gigahertz, we define 16 channels with 5 megahertz of bandwidth. Before we go any further, what can you tell me about the probable data rates between those 3? How would they probably relate? What happens to RF bandwidth as you increase data rate? It goes up, yeah. You're going to have a wider RF channel for faster data. So with a 600 kilohertz channel, I'm not going to be able to pass, all things being equal, pass as much data as I can over a 2 megahertz channel, and neither of those are going to pass as much as a 5 megahertz channel. Okay? So that's kind of the way we're looking at that. I said they learned, you'll notice they did use 2.4 gig, and that's trade-off. You know, they needed wideband data when they did this for some applications. But they also, notice what they did with the channels. They've got them set across here. These are all 5 megahertz. An 802.11 channel is 20 megahertz wide. And so they've got these spaced across here, but they set it up so that you actually have some sweet spots between. Channel 1, 6, and 11 are the most commonly used 802.11 channels at 2.4 gig. So if you want to minimize the likelihood that your Zigbee network and your 802.11 network that are in the same physical area are going to interact, stick to the channels that are between in there. So Zigbee 15, 20, and 25, or 26, for example, are less likely to interfere. Not immune, less likely. Okay. Now, what kind of things use them? Well, you see a lot of this stuff in residential. If you look at home automation catalogs, you see a lot of Zigbee. They may not call it that, but that's what they're using. And so you'll see things like thermostats that you just put on the wall, and you don't actually have to wire to the furnace. What you'll do is put a receiver on the furnace, and then let the control and the receiver communicate over Zigbee. You'll see things like alarm sensors. So I have my alarm control unit over here, speaks Zigbee. I have window sensors. They communicate over an RF link instead of me having to run wire pairs across that link. You know, pretty much anything along that line you can think of. Motion sensors, temperature sensors. I suppose you could get an interface so you could turn your coffee pot on remotely if you wanted to, probably. When you look into industry, you're going to see things like process control interfaces. Electrical substations are starting to use this for monitoring, things like that. Okay. Now, we're dealing with a protocol that is going to accomplish more complex things. You know, we're not just connecting a few peripherals here. For that reason, we're dealing with a protocol that specifies multiple frequency ranges. So our protocol stack is going to be more complex. For one thing, we have 2 physical modules. 868 and 915 share a module. They're closely enough related and close enough in frequency that that works. 2.4 actually has a different physical interface on it. The Mac in this deals, in addition to doing the framing and all those discussions we talked about, also deals with addressing. And the addressing for this, because we need to be able to separate networks, and have a group of machines here and a group of machines here, that addressing has to be more complex. I need to be able to refer to groups of machines to accomplish what this protocol needs to do. So we've got a little more capability in this particular protocol. The channels at 868 and 915 run at 20 kilobits and 40 kilobits respectively. If you need wider data than that, you can get 250 kilobits at the 2.4 gigahertz. The trade-off is you're going to go have a shorter range, all things being equal, and you have more potential interference. So, you have the ability to sort of tailor this to what your application is. Okay. So, whoops, that was supposed to fade in later. Sorry about that. For the moment, ignore the frame. I'll fix that before I post these. The network topologies that Zigbee supports are from the simplest to the most complex: star, mesh, and tree. Now, because we're accomplishing more complex things with this protocol, we have to kind of complicate how the world works. Whereas in Bluetooth, you saw the coordination of the network basically rested on the master machine, and all the others were just slaves. I've got one device I'm going to connect things to, and it's going to control who connects to it. We can't say that here, because I might have variations of that across several subnetworks. So I'm going to have something called a PAN coordinator. Actually, Bluetooth uses that term, but it's a pretty simple implementation. The PAN coordinator actually controls is not the right word, mediates communication. You guys have studied Ethernet, which is, remember, TSM-320, carrier sense, multiple access. What does that mean? Carrier sense means I listen to the network before I transmit. It's basically modeling human communication. I listen to the network before I transmit. If somebody's transmitting, I don't transmit. I don't talk while somebody's talking. Every station on the network does that, so the idea is none of us are going to talk at the same time. That's the multiple access part. Now with Ethernet, you've got a wired connection. And so detection of that time when both stations, we have two of us on a network, we both want to transmit, we both follow the rules, we listen to the network, both of us at the identical instant decide, oh, the network's clear, and we both start transmitting. We both follow the rules, but we've still done something that isn't going to work, which is both transmit on the network. That's a collision. The way Ethernet detects that is it looks basically at the power of the signal in the wire. Remember, power is area under the curve if you're charting voltage. Well, if I've got two stations transmitting, I've got more power than I do if I have one station transmitting. So I can actually make the interface card detect the power level, and if it's above what I expect to see, there's been a collision. And what that protocol does is say, okay, if there is a collision detected, both of you stop transmitting, wait a random amount of time, and then start that whole process over. Okay, works great. In wireless, and actually, I just realized I should have included a different piece in this graphic. I'll rebuild it before I put it out. In wireless, you have a couple of issues that deal with this. First off, I don't have a closed environment. In a piece of Ethernet cabling, I can very closely predict what the power on that wire will be for an Ethernet frame. It's going to have some variability depending on exactly what the frame's composed of in terms of zeros and ones. But I can predict pretty closely what it ought to be with a single station transmitting, and I can predict how it will change if I have more than one station transmitting. I can't do that with radio. What happens to a signal as I move further away from you? What happens to the power of that signal that I receive? It drops. So I don't have that benchmark for looking at power as a way to detect a collision. Okay? Number 2 problem. If I have 3 devices that are communicating, I could pretty easily end up in a situation where these 2 can hear each other and these 2 can hear each other, but these 2 cannot. This is a common enough problem that it even has its own name. This is called a hidden, sorry about my handwriting, hidden node problem, and I'll add this to the slide. Hidden node problem. Okay, if I'm doing that carrier sense, listening to the network, if I'm doing it here, I can hear both of these stations. So the process works. If I'm doing it here, process works. If I'm doing it here, the process works. The problem is, when I have this one and this one both wanting to communicate at the same time, they can't hear each other. So I can't do that collision detect because I have no way to hear the other station, and oh, by the way, even if I could, I have no way to reference what the power ought to be. You can't do this. You can't do collision detection on radio-based systems. So what we do is something called CSMA-CA, which is collision avoidance. There's several ways to accomplish it. Essentially, they all come down to some form of central mediation. If I want to transmit, some central authority gives me information about when it's okay to transmit. Now, that's as far as we're going to go into it in here. There are lots of ways to skin that cat. But the central authority provides that information. In Zigbee, that central authority is the PAN coordinator. The coordinator provides that mediation. Okay. So, in a star network, what the coordinator does is mediates media access and makes, your book calls it routing. I dislike that because we define very heavily that routing is a layer 3 thing and this is a layer 2 network. I'm trying to consistently refer to it in my notes as path decisions. I don't even want to use the term switch. Path decisions. If I need to communicate from here to here, I'm going to send that through the PAN coordinator. Okay? That's easy routing. The problem is I don't have any redundant paths. I know I'm right on top of time. Can you give me 2 minutes? Okay. I know I have no redundant paths. So if I lose one of these links, somehow I get cut off, I create an orphan that can't participate in this network. I can cure that by allowing connections between adjacent devices. I still have a coordinator in this network. There's the coordinator in the star network. And I put the wrong one, actually. This is the coordinator. It wouldn't really matter. Any one of those could be the coordinator. The coordinator still does that mediation function. But the communication can happen between multiple nodes, and we have redundant paths. I can cut one of those paths and still have communication. The price is that it's harder for the coordinator to make decisions on how a frame should travel across this network. Similarly, if I string a bunch of these together to make a longer network, make more paths out, I still have a coordinator. I'm still coordinating and mediating, but I've made that decision process about how to send traffic across this network harder. I've got one more piece I want to cover. We'll pick it up there Friday, and then we'll finish this one up and then go into Chapter 6. So if you would read Chapter 6 by Friday, and we'll go from there. See you guys. By the way, remember the conference. If you have a chance, stop by. I think it'll be worth your while.